So last time we learned about just light.
Light and waves, yep.
But this is like a unit on the atom.
This is chemistry class.
So
what are you talking
it's
about?
like a physics time.
Yeah.
What's up with that?
I don't know.
Well, you see, guys, the atom and light are kind of connected. Inextricably connected. So we're going to connect what we've been learning about light with the atom itself. And it really answers sort of a kind of a cool question. Where does light come from?
Light bulbs.
Something like that.
The sun.
Yeah, well, let's talk about how light works. So things you probably do or do not know.
Like Pink Floyd.
Pink Floyd, yeah. So if you've got light, and if white light goes through a prism, it separates into the colors of the spectrum.
Uh-huh.
So this is something that's true. You get that spectrum, and it's Roy G. Biv, right?
Mm-hmm. You'll probably learn this in elementary school somewhere.
Red, orange, yellow, green, blue, indigo, and violet. These are the colors it separates into.
In that order.
So scientists have known this for like ever. I mean,
my 5-year-old knows this.
Your 5-year-old.
Yeah.
So this is something that we know about light, but this teaches some interesting things. So here's an interesting thing that happens. If you take a tube filled with hydrogen gas, so this tube is filled with hydrogen gas, and then you pass this through a prism,
or some sort of refracting device.
Yeah, there's more than one way to do this. It splits up, interestingly enough, into only 4 specific colors. Or down here, in a more specific one, we can actually see scientists then measure the wavelengths of the light. Here we have 410.1 nanometers, and 433, 486, and 656. Where's the rest of the light? Where's this light and this light?
It's not there.
It's not there. So scientists have actually known about this phenomenon for a long time, but they couldn't explain it because this is only filled with hydrogen gas. So if it's only filled with hydrogen gas, there must be something about hydrogen that's causing this to happen.
Yeah.
In fact,
yeah.
You know, it's not just true about, say, hydrogen.
No, each element has its own individual fingerprint, if you will, of the amount, the wavelengths of light that are produced.
So if you did the same process with helium, you would find these lights. With iron, you'd find these colors. In neon, you'd find, and they're all different. And they've used that for some cool stuff, which we'll talk about in a minute. But what does that tell us about the atom? So why don't we
let's take a look at this.
Take a look at this, how this works on the video clip. So folks, here I am looking at, I've got a spectral tube right here. So I'm going to apply a whole bunch of electricity. This is like 10,000 volts or something like that. Do not put fingers in sockets when you turn on.
Duh.
That's one of those dumb moments. And in this tube, let me put it out here, I have argon gas. So this is a tube filled with argon gas. I'm going to turn it on, and it's going to make a light. It's like basically a light bulb. You've probably seen neon lights. And so as I turn it on, it makes a really cool purple color. All right. Now, the thing that's kind of cool that you can do is that you can take your cool glasses that I was wearing for our lightsaber fight, and these cool glasses then break up the light into a spectrum of colors. Okay. And so we'll see if we can do that with our, does that make us do
it? It does.
And so does it split it apart?
Uh-huh.
Oh, how cool is that? So you can see as you're looking. What do you see, Mr. Sandy?
I see a bunch of different colors. I got a purple line and a green line and maybe like a red line and possibly some yellow in there.
Okay.
But we can see distinct colors that are not in the original color of the light. We have the colors all split up.
Okay. Now, let's now do that, and let's take a shot.
Oh, nice.
Woo! Okay, that was no fun. All right, and I have another spectral tube, and you've seen these before. This one's filled with xenon gas. And so I expect to see something different. You'll see lines like we just did a minute ago, but you should see different lines because it is a different element. We'll talk about that in a minute too. All right.
Ooh, okay.
Blue color.
Nice blue color this time. I put on my glasses.
So Mr. Sam's is putting the glasses on the...
Yeah, it's not quite as good as the last one. We got a little light coming in through our door there, but I've got a blue line, looks like a little bit of yellow, maybe a little bit of red. These are not quite as distinct as the last one.
Yeah, I probably have too dim of a bulb. But I think you get the idea that every element has its own set of spectral lines. And actually the more interesting thing is not the lines that are there, but the lines that are not there. Why don't we see all Roy G. Biv? Why don't we see those?
We'll talk about that.
And we'll talk about that. That was really cool, Mr. Sam.
Yes,
very, very cool. So now the next question I want to ask Mr. Sams is, well, then, so what? So you
Yeah.
know all this stuff, how can it be used? Well, guess what? Have you ever been to the sun, Mr. Sams?
No.
No. How come?
It's kind of hot there.
Yeah. See, the sun is like I think the surface of the sun. I know this. It's about I think it's like 8,000 Kelvin, maybe 6,000. Well, 6,000 to 8,000 Kelvin. That's hot.
Oh.
It would like melt you. I think it would boil you. It would be, it would be very hot. Not a very good thing. So guess what? If you point like a spectroscope and the refractor deal at the sun, you guess what you get? You get this pattern right here. This is from the sun, and they draw these graphs. We care about these graphs actually, and they can actually determine which particular elements.
I've been saying refraction, haven't I? It's diffraction.
Yeah,
refraction.
I don't
know.
Yeah, it is diffraction. You're diffracting.
Okay.
And so this is, you can like point these things at different stars.
Yeah.
And when you point them, you can say, well, that star is mainly made of hydrogen and helium, which is most stars are. But you can find all the other elements.
Yeah, there's really cool. When I lived in California, there's a place called the Griffith Park Observatory, and they have a big solar telescope there. And you can actually look through this little doohickey, and you can see the spectrum from the sun, and you can see these little lines that are distinctly there that tell you what the sun is made of, or what your atmosphere is made of, things like that. So
that's cool. Yeah. The other thing that it tells us about the atom is it actually tells us the atom has specific energy levels. And so here are the colors from a particular element. I'm not sure this is a real element. But if you remember, the atom is remember, the atom actually has specific energy levels, which they call orbitals. And an electron can move from the E2 to E1. Now, if you drop it from E2 to E1, it produces a
high energy to low energy.
Higher energy to lower energy.
So it has to release that energy somehow.
And it releases it, in this case, as red light. Or if it falls from, say, E3 to E2, that produces a specific color of light.
Okay.
So that's important to understand. So this kind of answers the question, where does light come from?
The sun.
No.
The light bulb.
No. It comes from electrons moving.
In the light bulb.
Well, yeah.
And in the sun.
Yes, you see. Atoms, everything is made of atoms. And all atoms have electrons. And electrons move. Now, move is sort of a weird term. We'll talk about that in a minute. But let's say, for the sake of argument, it moves. When it falls from E2 to E1, it gives off a very specific color of light. Let's say this is 621 nanometers or something like that. Should it be shorter?
Long wavelength, low energy. Yep, so that's probably 700-ish.
Let's call it 700 nanometers, whatever. So that's 700 nanometers. And if it falls from here to here, it gives off purple light. Maybe it's 450 nanometers. But it's a very specific color of light.
Right.
And so when the electrons fall from a higher energy level to a lower energy level, that's where light comes from. So here's what I want you guys to do. I want you to pause the video, and I want you to write a quick little sentence or two about where light comes from. Okay, so now let's kind of fill in our blank.
Okay.
Light comes from
electrons falling.
Now we say falling because
they don't
in
really
quotation
fall.
marks.
Because they don't physically drop from one to another. It's like it's in the higher spot and then it's in the lower spot.
Let's talk about that in a minute. I think I got a slide on that. So more specific, electrons must first be
excited.
Woo-hoo-hoo! You have to get them. They like to live at a lower energy level, which we talked about before.
Yeah.
And then they must fall.
Not really fall, but go back down
quotation
to
mark
a lower.
Back to a lower energy level. Okay.
Yep.
So what does this tell us about the atom? Electrons are, now here's a big fancy word, quantized.
What that means is they can only be in specific places, though they can only have specific energies. They cannot have energy in between those specific values. And to expand that, the electron cannot be anywhere in between those energy levels. It is either in this one energy level or it is in the other energy level, never in between.
To illustrate this, Mr. Sams, I think we probably should do something.
Okay.
All right, so let's watch a quick little video clip here. All right?
So we want to learn about where light comes from. Well, light comes from atoms. And so I'm going to be an electron. Do I look like an electron? Okay, I am. An electron in an atom. And Sarah over here is going to just be the energy source. So she's going to hit me. Okay, not physically, but she's gonna throw things at me. Okay, so Sarah, go ahead. She throws to me. Oh, it hit me. Oh, I jumped up. I'm on another higher energy level, and I usually don't like to live at a higher energy level, so I will. So what's called absorption. I'm going to emit this light, throw it back to Sarah, and as I do that, I fell to the ground and I emitted some energy. A specific color of light. That was a color of light that went out. So she hit me with the tennis ball. Now she's going to hit me harder with the duct tape. Oh, ooh, it hit me, knocks me way up here. Oh, I'm far from the ground. I don't like being far from the ground. So now the energy needs to come outside of me. And so I want to get rid of this. I'm going to throw it away. This will be a higher energy. So there is like purple light. And I'm going to throw this back to Sarah. And boom, I fall back down to the ground, hurt my knees. And no, I didn't. And I emit a greater amount of light. That was emission when I threw at Sarah, and it was absorption as I went up. Right? Got hit. I got absorbed. Absorption. Emission. You got it? Good.
Well, that was pretty cool, Mr. Sims. I think that hopefully helps understand. It's kind of weird. It's either here or here or here, but never in between. That's a weird thing to do about Mr.
Yes.
That is like, are you sure? Yeah. Well,
Yeah.
we are. Okay.
Hey, look, it's Star Trek.
Hey, Star Trek.
Fire go torpedo.
Yeah, that's the whole torpedo. But it's like light. So, hey, here's a photon. A photon is one of the particles.
Hold it, describe path of light.
So electron fall, and that's what we just learned about. It
Ball.
gives off one photon of light. Now, of course, when you turn a light bulb on, it gives off many photons because many electrons are being excited and falling down, excited and falling out. So it's a particle of light or a packet of light, is what you're saying. So
Yeah. Just chunk of energy.
and it's way smaller than light.
Yeah.
So, folks, that's where light comes from, and that's the kind of concept here. Way cool.
Beam me up, Scotty.
All right, can you give me more?
I'm giving a rush, he's got, Captain.
Okay, bye.